Welcome to my YouTube channel, The Next Level Topics and Contents. Now, in this topic, we will see about the Zeeman effect. Zeeman effect. For this topic, I have taken the system, the quantum mechanical system, that is two-dimensional isotropic harmonic oscillator, and I have selected one level, that is first excited level of this system. Excited level of this system. So for this topic, that is Zeeman effect, the system is two-dimensional isotropic harmonic oscillator. What is this? For this system, the potential operator is half m omega square r square, where r is the plane polar coordinate and r square is nothing but x square plus y square. X and y are Cartesian coordinates. So the boundary of this system is this half m omega square r square. Now, isotropic, this is means omega x is equal to omega y, and I have taken this omega. Sorry. So the potential is half m omega square r square. Now, what is first excited level? The first excited level of this system, that is given states, are psi x is equal to r01 r cos phi and psi y, that is r01 r sin phi. These are the states of first excited level. Okay. These states are real states. So these are given in questions. You say that these are given in question, that psi x is this, psi y is this, and potential is this. Then what is the effect of magnetic field on this system? What is the effect of magnetic field on the level of given system? This is our question. Okay. So these questions become a degenerate perturbation state problem. Degenerate perturbation state problem. Degenerate perturbation theory means what? Degenerate perturbation theory means the perturbation applied on a level having degeneracies 2, 3, 4, etc. So this is the problem of degenerate perturbation state, perturbation theory, or called degenerate perturbation state problem. Now, for this, first of all, we know what are the wave function and what are the energy of this system. What are the energy of the state of the system? So, the energy of the states are given by n, and that is for given by two quantum numbers, that is n and m, and n and m by this combination, that is n mod m plus 1 h Dirac omega gives the energy levels. Okay, where n is equal to 0, 2, 4, 6, etc. and m is equal to 0, plus minus 1, plus minus 2, etc. So, for satisfying the Schrodinger wave equation, there are two quantum numbers that are n and m, and which are belonging to energy and also the wave function, that is psi and m. So, the energy levels, the ground energy levels, ground energy levels, the ground energy level, that is n is equal to 0 and m is equal to 0, that is least energy states. So, least energy of this state is equal to h Dirac omega, means ground level contains only one state psi 0 0 having the energy h Dirac omega. So, this is non-degenerate state, non-degenerate state. Okay, but I have to see the degenerate perturbation theory. So, I have selected the first excited states. So, for first excited states, the energy level is n, and this is based on two quantum numbers n and m, and the combination is n mod m plus 1 h Dirac omega, and n is equal to 0, 2, 4, and m is equal to 0, plus minus 1, plus minus 2. So, the next higher level is equal to the 2h Dirac omega, because n plus mod m, that is next highest after 0, is 0 and plus minus 1. So, this is equal to the energy levels is equal to 1 plus 1 h Dirac omega, that is equal to 2h Dirac omega. But this energy level consists two states, and that are 0 plus 1 and 0 minus 1. Okay. So, here 0 plus 1 and 0 minus 1 are the two degenerate states of first excited level. Now, these states are written by 0, 1 and e to the power I phi, and this is written by 0, minus 1 e to the power minus I phi. By the linear combination of this gives R01 e to the power I phi and R0 minus 1 e to the power minus I phi. This gives the two states psi x and psi y, and this is the real function, and this is unperturbed state. These are unperturbed state. So, This is given as R01R and cos phi and R01R sin phi. These are the states given for this problem. Okay, I have taken the real wave function. We can work with the imaginary function, but in question, these are given things. So I proceed by taking these functions. Now, the for perturbation, degenerate perturbation theory, the perturbation H dash is given as epsilon Lz, and epsilon is equal to QB by 2 mu C into Lz is equal to minus IH direct del by del phi, because the wave function is in R phi term, that is in plane polar coordinate form. So the operator is also taken in this form, plane polar coordinate form, and in this term the H dash, that is perturbation is given as this much. Lz is the operator. Lz is equal to minus IH del by del phi, and epsilon is the strength, depends on a strength of magnetic field, and this is equal to this much. Q is the charge, B is the magnetic field, and mu, that is the, for single body you can take this m, and for more than one body you can take the reduced mass. So here this is given as mu, or you can take m. This is for combined body system. Now, hence up to this we have selected the wave function, psi x and psi y, and these are 0, 1 radial function, and the angular function is for x, this is cos phi, and R0, 1, this is radial function of this psi x, and this is for psi y, radial function is same R0, 1, and this is sin phi. Okay. And H dash is equal to epsilon minus IH direct del by del phi, because this is constant term. So here there are two wave functions, and combinedly I have to apply the magnetic field on these states. So this becomes the degenerate perturbation theory problem. Now, in case of degenerate perturbation theory, how can we calculate the first order energy correction and wave function corresponding to this energy? Wave functions corresponding to this energy. These are the output of our taken problem. So we want to calculate first order energy correction, and after that what will be the energy of the energy of the states, and what are the wave function for the corresponding energy. So this becomes the problem of degenerate perturbation theory. Now, what is the process for solving this question? For any degenerate system, for example, if degeneracy is 3, let's say wave functions are psi1, psi2 and psi3. These are the wave functions, psi1, psi2, psi3. And since this is degenerate, these are degenerate system, so having same energy, and this is same unperturbed energy. Now, after applying the perturbation theory, we get a 3/3 determinant, that is the secular determinant, and this determinant contains the elements H dash 1 1. You can write 1 2 3, 1 2 3, 1 for this wave function, 2 for this wave function, and 3 for this function. So easy to write. H11 minus E first order correction and S11 H dash minus, and H dash is for 1 and 2 wave function, and E1 S12. Similarly, this becomes H dash 13 minus E1 S13, and for this row the first element is H dash 21 minus E1 and S21, and the last element becomes you can write this in similar way, and the last element is H dash 33 minus E1 S33, that is equal to 0. This is the secular equation. Now, secular determinant. By solving these determinants by taking the different integrals here, we can calculate E1. And since this is 3/3 determinant, so we get the 3 values of E1, and if we take alpha, beta and gamma, these are the 3 values of E1. This shows that how the degenerate levels split after the applying magnetic field, after applying the magnetic field. So here the degeneracy is only 2. In my case, in taken problem, that is degeneracy is only 2, and these are the states are psi x and psi y. So under the process of degenerate perturbation theory, we can write here psi x, psi y, psi x, psi y, and write down the elements. That becomes h dash, and this is 1, this is 2, then this becomes 1 1, E1, S11, this is H dash 1 2 minus E1 and S12, this is H dash, this is 1 and this is 2. So this is 2 1 and minus E1 S21 and H dash 2 2 minus E1 S22. Now, what are these integrals? By putting the value of these integrals, we get E1, that is first order correction in energy. So, for calculation, first of all, I have to see the H dash N1. What is H dash N1? 1 1. For this, I have to normalize the wave functions. After that, we will able to calculate these integrals, that is h dash 1 1, h dash 2 2, h dash 2 1, h dash 1 2, and S11 is equal to S22 and S12 is equal to S21, because these are the eigenvalue problem. So here S11 and S22 are normalized function, gives 1 value and this gives 0 value. You can check here. So I have to know about these integrals. Okay. For these integrals, first of all, we want to normalize the function. So psi x is equal to R01 and cos phi. And what is R01? R01. This is equal to R times e to the power minus alpha R square by 2. And here alpha is equal to m omega by h direct, or mu omega by h direct for the combined body system. So the wave function becomes n r e to the power minus alpha r square by 2 cos phi. What is the normalization constant of this function? So for normalization, I have to write the total probability for this state is equal to 1. And for total probability, the expression is psi star psi, and d tau, this is equal to 1. And what is d tau here? D tau is nothing but r dr d phi. I have previously proven this is in video 6. You can see in video 6 on my YouTube channel. So here the psi x star, this is real function, so complex conjugate doesn't affect this function. So this is equal to n square, and this gives r square e to the power minus alpha r square by squaring the function, and r dr, this is radial part also, 0 to infinite, and the phi part becomes cos square phi d tau. D tau is d phi. Okay. And 0 to 2 pi, because r varies from 0 to infinite and phi varies from 0 to pi, 2 pi. So this integration must be equal to 1. What would be the integral value of this part? The integration gives gamma 4 by 2 divide 2 into alpha to the power 2. Okay. And this part is the cos square phi. So upper limit is 2 pi minus 0 by 2. Because this gives sine 2 pi, and sine 2 pi becomes the 0 after putting the integration. You can do this. This is equal to 1. So after the calculation, we get 2 here. This is equal to this will be equal to 1, because this is equal to factorial 1. This is equal to 1. And now this becomes n square pi by 2 alpha square is equal to 1. So n is equal to 2 by pi, the root, and alpha. This is the normalization constant for given wave function psi x. Okay. Verify this. Just a minute. Okay. This is the normalization constant. Now, for psi y, that is for psi y is equal to, similarly, R01. Here also R01 is equal to R times e to the power minus alpha R square by 2, and y that project the sine phi. Okay. So psi y is equal to this much. Now, for normalization here, if this is a normalized function, so I put n here, and this becomes n square. Similar integral arise here, that is r square e to the power minus alpha r square r dr 0 to infinite, and the angular part becomes sine square phi d phi 0 to 2 pi, and this becomes 1, because total probability becomes 1. That is the concept of normalization. So again, n square and integral of this gives gamma 4 by 2 into alpha to the power 2, and this function again gives 2 pi minus 0 by 2, and integration is also gives sine 2 pi, and the becomes the 0. So this is only the term comes from this integration, and this is equal to 2. So again this is equal to n is equal to 2 by n is equal to root under 2 by pi. Okay, this value root under 2 by pi, root under 2 by pi into alpha. This is the normalization. So normalized function becomes psi x is equal to root under 2 by pi alpha into r into e to the power minus alpha r square by 2, and for x this is cos phi, and similarly in psi y this is equal to root under 2 pi into alpha into r e to the power minus alpha r square by 2, and here this is sine phi. So we got the psi x and psi y here, normalized states. Now I have to apply the magnetic field on these functions. So first of all, I have to calculate h dash 1 1. What is this? This is equal to, this integration is equal to psi star x, and the operator is h dash. Now again this is psi x and d tau. What is this value? So h11, this is equal to psi x is what? Psi x, we have seen that psi x is equal to root under 2 by pi alpha into r e to the power minus alpha r square by 2. Okay, by taking the complex conjugate of this, but this does not affect this, and h dash is equal to epsilon times the LZ operator, and psi x is again this function e to the power minus alpha r square by 2, and here this is equal to cos phi, and this is equal to cos phi also, and d tau is r dr d phi. So by separating this integration into two forms, that is radial form and angular form, we get, and this is the becomes a square of this, because here normalization also gives this same term. So this becomes 2 by pi alpha square into the integration becomes the radial part does not affect by these perturbation. So radial part becomes r square, that is r cube here, and e to the power minus alpha r square dr. Okay, and this goes from 0 to infinity, and now the epsilon, this is also constant, and Lz gives minus IH direct del by del phi. So del by del phi and cos phi here, and this cos phi is also taken here, cos phi, and d phi 0 to 2 pi. Now this integration becomes, we will see this integration later. First of all, see the here, that is 0 to 2 pi, and this is minus IH direct, and this is cos phi, and differentiation gives minus sin phi, so becomes minus sin phi d phi. Okay, so if this function, if this integration doesn't vanish, then we will calculate this, otherwise this is not required. So 0 to 2 pi and IH direct and cos sin phi into cos phi into sin phi, this is becomes sin 2 phi by 2 d phi, and the integration of this gives cos 2 pi by 2 and minus sin 0 to 2 pi. So we see here that this becomes cos 4 pi minus cos 0, and this gives 0 because cos 1 and minus cos 0, this gives 1. Hence, psi h dash 1 1 gives 0 value. Similarly, h dash 2 2 also gives 0 value. You can check this because here radial part is same. This is radial part, and if we ignore this, then we come for the angular part. The angular part for this function, that is here angular part is sin phi. So integration of this angular part becomes sin phi into minus IH direct in similar fashion, that is del by del phi and another sin phi d phi. So this is 0 to 2 pi, and here this is 0 to 2 pi and sin phi, and this also becomes cos phi and d phi, and now the same process, this becomes 0 also. So we see that h22 and h dash 11 are 0. Now we go for h dash 12. What is h dash 12 here? So for this h dash 12, the first of all we take the wave function 1, that is root under 2 by pi alpha and r times e to the power minus alpha r square by 2, and for this 2, that is also same term in radial part. So this becomes a square and r dr. This is the d top part, the radial d top part. So this is 0 to infinity integration. Now for phi part, here for phi part, for 1 this is cos phi and for 2 this is sin phi. So this becomes cos phi into minus IH direct del by del phi sin phi, okay, and d phi, and another term in this perturbation is epsilon. So epsilon is a constant taken here. Now what is the integration of this function, this integrand? So this becomes 2 by pi alpha square, and this is equal to r square e to the power alpha r square, and again this is r, so plus 1 and dr 0 to infinite, and this angular part becomes cos phi, and this is minus IH direct, and sin phi differentiation gives cos phi, and cos phi, this is equal to d phi. So here 0 to 2 pi. Now here the integration of this is equal to 2 by pi alpha square, and this is the gamma function, so this is equal to 4 by 2 into 2, and here this is alpha, so alpha to the power 2. Now this is equal to minus IH direct, and now this is cos square phi, and cos square phi gives integration, that is 2 pi by 2. Okay, you can check here. Check. This is 2 pi by 2. So by solving this, we get this pi on here, this is also on here, and this is equal to 1. So this becomes minus IH direct epsilon. So H12 is minus IH direct epsilon. This is the second element of first row. This is the second element, H12 minus E1 S12. S12 is 0. So only H dash 12, this is our second element. Hence the third, that is the first element of second row, that is H dash 21 is equal to what? So H dash 21, this is equal to 2 signifies for sine phi and 1 signifies for cos phi. So radial part is same here. Radial part is same. That is equal to root under 2 by pi alpha and r e to the power minus alpha r square by 2 r dr and square of this function, and this is epsilon time 0 to infinite, and phi term is this is r dr. Okay, so the phi term is here sine phi minus IH direct, differentiation is del by del phi, and that is for cos phi. Now this is d phi 0 to 2 pi. Here this integration gives the same value, only difference is that here minus IH direct, and by differentiation this gives plus IH direct. So this is plus IH direct and sine square phi, this gives sine square phi, and sine square phi, integration of sine square phi d phi also gives the same value as cos square phi for this integration limit, that is also the 2 pi by 2. Yeah. Hence the integration finally gives h dash 1 to 1 is equal to 1 is equal to epsilon IH direct, only sign difference, that is difference in sign here. So h dash 1 2 is equal to minus epsilon IH direct, and h dash 2 1 is equal to plus IH direct epsilon. Okay, but h11 and h12 H22, these are equal to 0, and S11 and S22, these are equal to 1, and S12, S21, this is equal to 0. So we have taken these integral values for solving the circular determinant. So the first element of the first row becomes H dash 11 minus E1 S11, and H12 dash minus E1 S12, and H21 dash minus E1 S21, and H dash 22 minus E1 S22 is equal to 0. Now here we have calculated the H11 value. This is equal to 0. This is equal to 0. So this determinant turns out into 0 minus E1 and S11 is equal to 1 for normalized function. This is 1. And now H12, this is equal to H12. I have calculated that epsilon IH direct and minus this is E1 and this is equal to 0 because orthogonality taken here. So H21, this is equal to also the plus epsilon IH direct, difference in sign here, and minus E1, and this is also orthogonal, so this becomes 0. And now here this is equal to H22, this is equal to H11, that is 0, and minus 1, S22, that is normalized functions. For normalized function, this is equal to 1. Now, this determinant becomes minus E1, that is the required value for our problem, and minus epsilon IH direct, this becomes 0, and now this is plus IH direct, and this is equal to minus E1 and equal to 0. What is the value of E1? So, by solving this, that is E1 square, okay, and this is equal to minus, so plus, this is equal to plus EIH direct square and equal to 0, equal to 0 here. So E1 square is equal to minus EIH direct square, and this gives E1 is equal to plus minus, because under root this value gives IH direct plus minus. So by combining this, becomes EH direct and minus EH direct. These are the two values we got here. So the energy eigenvalue of these functions taken into account, that is degenerate states of isotropic harmonic oscillator under magnetic field, gives the first order energy correction. This is equal to EH direct and minus EH direct. So our expression for energy after this correction becomes E01, that is plus minus 1, all this plus minus 1. This is in unperturbed state gives energy 2H direct omega. But after the applying magnetic field, that is perturbation, ELZ, we got two eigenstates and two states, and these are one having the energy 2H direct omega minus EH direct, and another having energy 2H direct omega plus EH direct. So, the energy cannot be changed here. The energy of the system cannot be changed because for two states, here energy is also 2h direct omega plus 2h direct omega, that is 4h direct omega. But here the extra term my EH direct is subtracted and here this is added. So, the total energy of this system is again 4h direct omega. But these states are splitted by the difference of energy, that is, what is the difference here? Difference of energy, that is 2EH direct. This is the difference in energy. Okay, this is the answer of our problem. Now, you can calculate the energy values for wave function for these energy outcomes. The energy outcomes are 2h direct omega plus EH direct, and one is 2h direct omega minus EH direct. So, what are the wave function for these states? This is our question, and that we will see in next video, that is video number 8. Okay, thank you for watching.